Now that we've looked at how we figure out mole ratios using our balanced equations, and then we use that to help us do conversions between moles or between mass and moles, now we're going to apply some more concepts to this. So we're going to take a look at limiting reactants, percent yield, and we'll also calculate theoretical yield, as well as looking at excess reactants. So if we go back to kind of cooking examples and pancakes. So we had talked about before, hey, if you're making pancakes, you need a certain amount of flour, a certain amount of eggs, a certain amount of baking powder in order to make 5 pancakes. So if we wanted to look at the problem and we said, hey, we have 3 cups of flour, we have 10 eggs, we have 4 teaspoons of baking powder, how many pancakes could we make? So as you look at this, what do you think? How would you figure it out? Well, probably you'd look at each ingredient and you'd figure out, well, how many pancakes can I make from that ingredient if I have that much? So if we look and kind of use like we did before and we say, here's our general mole ratio. If we had 3 cups of flour and we said, well, for every 1 cup of flour, we can make 5 pancakes. So we can make 15 pancakes from that. If we had 10 eggs, for every 2 eggs, we can make 5 pancakes. I'm just going to say 5p. So in that case, then we can make 25 pancakes. Or if we had 4 teaspoons of baking powder, and for every 1/2 teaspoon or 0.5 teaspoon of the baking powder, we could make 5 pancakes, and we could get 40 pancakes. So we would say, well, we're going to run out of flour first. So flour is the limiting reactant, and the pancake is our theoretical yield. So this is how much we theoretically could get. The flour is going to be the limiting factor in this scenario. So if we had all of this and we say, all right, so we can make 15 pancakes, if that's the case, how many eggs will we have left over? So if we're making 15 pancakes, how many of the eggs will actually be left over? So what we would do is we would take a look and we would say, okay, well, I know that I have 15 pancakes. For every 5 pancakes, I'm going to need 2 eggs. And so then I would multiply that. So I'd have 30 divided by 5. So I'd have 6 eggs needed. And I started with 10, so I would have 4 eggs left over. I can do the same thing with the baking powder. And what's cool about this is that I could also go from the 3 cups of flour. So that's my limiting ingredient. So I could say 3 cups of flour. And I know that for every 1 cup of flour, that I would need a 1/2 teaspoon or 0.5 teaspoons of the baking powder. And so 3 times 0.5, I would use 1.5 teaspoons used. So that means that I would have 2.5 teaspoons left over. I would get the same answer if I started with pancakes and looked at the teaspoons, and I'd have the same answer for the egg if I started with the flour instead. So all of these relate, so there's more than one way to get to the right answer. So whenever we then would be looking at actual yield versus theoretical yield, we could say this, we'll come back to this, like say that we only got 11 of the pancakes because you dropped some or you burned some. Then if we got 11 out of 15 pancakes, then we would get a 73% in terms of our percent yield. So take a minute, you can go ahead and write down these definitions. Limiting reactant, the reactant that makes the least amount of product. Excess reactant, reactant that's left over after the limiting is used. Theoretical yield, the amount that you expect to be produced. Actual yield is what you actually get, because there's sometimes some they're often not 100% efficient in terms of chemical reactions. And then we can determine our percent yield by looking at our actual yield versus our theoretical yield. So in order to determine the limiting reactant and theoretical yield, and therefore then kind of relate that to percent and excess reactant, the first thing that we need to do is we need to balance our chemical equation in order to determine the mole to mole ratios so that we can see what those ratios are. From there, we can calculate the amount of product that would be made from each reactant. So calculate the amount of product that can be made from each reactant. And the reactant that forms the smallest amount of product is going to be the limiting one. And then the amount of product that is formed by the limiting reactant is going to be the theoretical yield. So we'll run through a few examples. You can do a few with me. You can do a few on your own. Feel free to skip through the video if you feel comfortable and confident with these. And if you don't, then you can listen to what I have to say for each of the examples, and hopefully that will help you to gain more understanding. Okay, so for our first example, here's our equation. It's already balanced for us. And so if we start with 0.552 moles of aluminum and 0.887 moles of chlorine, what's the limiting reactant and theoretical yield of AlCl3 in moles? So for this one, we would have 0.552 moles of aluminum. We have 0.887 moles of chlorine. So we just need to go ahead and use the mole ratios to convert these to the moles of product. So 2 moles of aluminum for every 2 moles of aluminum chloride. And so this would be 0.552 moles of aluminum chloride. And we can also look at the chlorine. And so we'd have 3 moles of chlorine for every 2 moles of aluminum chloride. And so we'd get 0.591 moles of aluminum chloride. So 0.552 is the theoretical yield. And aluminum is going to be the limiting reactant. Okay, let's do another example. Okay, so we're going to go ahead and take a look at what's the maximum amount of ammonia in grams that can be synthesized or made from 45.8 grams of NO and 12.4 grams of H2. So let me go ahead and write down our molar masses. So I have 30.01 grams for NO. For hydrogen gas, 2.016 grams per mole, and ammonia is going to be 17.034 grams per mole. Okay, so if we're going all the way from mass to mass, then what we can do is we can say, all right, well, we start with 45.8 grams of NO. We're going to convert that into moles. So 1 mole of NO, 30.01 grams. Use our mole ratios. So 2 moles of NO will be 2 moles of NH3. And then convert to grams. 1 mole of NH3, 17.034 grams of NH3. Then we'll do the same thing, 12.4 grams of H2, convert that to moles. Use our mole ratios. Convert to grams of NH3. Okay, so with this, if we do the math on this, then we would get that for NO, we would end up producing 26.0 grams of NH3 versus 41.9 grams of NH3. So this smaller number is the yield, and NO is going to be the limiting reactant or the limiting reagent in this example. Here's another example. We're going to use this example for limiting reactant and theoretical yield, like we've been doing, and then we'll tie in problems with excess reactant and percent yield. Okay, so molar masses of everything. Sodium is 22.99 grams per mole. Chlorine is, chlorine is 70.9 grams per mole. And 58.44 grams per mole for sodium chloride. It's our job now to figure out the limiting reactant if we have 53.2 grams of Na and 65.8 grams of Cl2. So if you'd like to do this yourself, go ahead and pause the video and then check your work. We'll start with our grams of sodium and convert to moles. Use our mole ratios. Convert to grams of NaCl. Make sure all of your units cancel. Multiply and divide across, and you would get 135 grams of NaCl. Repeat the process for chlorine. Molar mass. Mole ratios. Convert to with molar mass of NaCl. Make sure all of your units cancel. Multiply and divide across, and you would get 108 grams of NaCl. Now, what I did want to note is that I did go to grams in this case. If you were only determining, and it did not say, you could also determine the limiting reactant by stopping at moles and saying the theoretical yield in moles. In this case, what we find is that our theoretical yield is going to be 108, so that would be the theoretical yield. And then the limiting reactant is going to be the chlorine. Okay, so given this, how would we calculate the excess reactant or excess reagent? So how much of the excess reactant will be left over? So in this case, what's being left over and the excess is going to be sodium. So we're wondering how much sodium is going to be left over. So in order to do this, we can use the limiting reactant to determine how much of the excess reactant you would need to actually completely react, and then subtract from whatever is given. So let's just go ahead and relate chlorine and sodium together. So we will do this. So we have 65.8 grams of chlorine. We're going to use the mass of chlorine again, so 70.9 grams of chlorine, 1 mole of chlorine. We're going to now do the mole ratio between chlorine and sodium. So 1 mole of chlorine is equal to 2 moles of sodium. And then we'll convert to grams since that's what we have our measurement in. So that would be 22.99 grams of sodium here. Make sure all of the units cancel and that you've done your ratios correctly. And so in this case, we would say that we need and require 42.7 grams of sodium is needed. So we'll subtract that from what we have. 53.2 grams of sodium is what we have, minus the 42.7 grams of what we actually need or what we use. And so we would have 10.5 grams of sodium excess or left over. after this reaction. All right, so finally, let's take a look at percent yield. And so percent yield is going to be just simply the actual yield over the theoretical times 100. Okay, so in this case, whenever we calculated our actual with the limiting reactant, we got that we would have 100 and, oops, sorry, that's the, what am I doing? We calculated 108 grams. That's the theoretical. So 108 grams of sodium was the theoretical from the first part of our reaction back here. And so we're saying, well, that's how much we expected to get, but we actually only got 86.4 grams of sodium. And so for the grade for sodium, or the yield for sodium in this case, is 80% yield. Okay. All right, so I do have several more examples for you, and we are going to take a look at this one. So we're going to take a look at copper. And this one is similar to how we did the reaction with sodium. So we want to figure out theoretical yield, percent yield, the amount of excess reactant left over. So we're just going to give you the whole problem here. So we have 11.5 grams of carbon reacts with 114.5 grams of copper 1 oxide, and we get 87.4 grams of copper. This here is the actual yield, and so we'll use this for the percent yield. Let me go ahead and give you some molar masses. So copper is 143.10 grams per mole. Sorry, the copper 1 oxide. Carbon, 12.01 grams per mole, which you would know. And then copper, 63.55 grams per mole. So start by looking at the limiting reactant. And so let's look at that first. So we'll take what we have. We have 11.5 grams carbon, molar mass of carbon, mole ratio, and we want to look at copper that's formed. I'm just going to go ahead and convert it to grams. I'll make sure my units all match up, and I will go ahead and cancel that out. It got a little wonky down here, didn't it? So 1 mole divided by 12.01. And so our answer for this would be 121.7 grams of copper. We'll do the same for copper 1 oxide. Mole ratio. Molar mass. Multiply all that across, 101.7 grams of copper. Again, use your units, including the chemical formulas, so that you make sure that you are doing it correctly. So 101.7, that's our theoretical yield. And our limiting factor is the copper oxide. So this is going to be the limiting reactant, which means that the carbon is in excess. So the carbon is in excess. Okay, so if we want to calculate percent yield, from the prior screen, we said that we had the actual yield, which was 87.4. So actual over theoretical. So 87.4 grams of copper is what we got. We were expecting 101.7. So if we do those calculations, our percent yield in this case is going to be that we have 85.9% yield. If we're looking at how much carbon is left over, we're going to take our original starting for copper 2 oxide, which would be 114.5 grams. Convert that to moles. And then we'll relate that to the carbon. So if we look back at the equation, it's a 1-to-1 ratio. Oops, that's supposed to be C. And then go ahead and take that to grams. So that will give us that we used or need 9.61 grams of carbon are required. So we have 11.5 grams of carbon minus the 9.61 grams of carbon that's used. Means that we would have 1.9 grams of carbon left over. And so that would be your excess reactant. Here's your final example. I'm going to go ahead and give you all of the molar masses, and then why don't you give it a try on your own and you can take a look at the answers. At this point, you've determined that the theoretical yield is 126.7 grams of iron, and that the limiting reactant is carbon monoxide, while the excess reactant is iron 3 oxide. If we wanted to calculate our percent yield, 87.4 grams of iron over 126.7 grams of iron, which is the theoretical, times 100, this would give us a 69% yield. If we want to determine how much iron 3 oxide is left over, We can do it one of two ways. So we can either use the theoretical iron or the amount of CO to use. So I'll do it with the carbon monoxide, 95.3 grams of carbon monoxide. Go back to the balanced equation and you would find this mole ratio of 1 mole to 3 moles. Get to grams. Make sure your units are canceling out. So we would use 181 grams. We started with 185 grams minus the 181.1 grams. And so we would have 3.9 grams of Fe2O3 that we have left over. We'll pretend that this was 185.0 just to make our sig figs work out. All right, so I hope that made sense. You're going to do some practice problems, mostly finding limiting factors and then percent yield. I do ask a few questions about the amount of excess reagent left over. Let me know what questions you have, but go ahead and give those problems a try.